Now we are going to discuss another topic called complexity analysis. So through this topic, you would learn how to theoretically reason about the running time of a given program. Because when we are writing programs, it is not sufficient to just be happy about a few chosen inputs and we see that the program functions properly for those chosen inputs. But the question is really how the algorithm is going to behave as as the inputs, let's call it as the number of inputs approaches infinity. Which means that if I increase the number of inputs to such a degree, into astronomical proportions, is your program capable of giving the output still? That's the key question that the computer scientist has to answer. And without answering that question, we cannot just go ahead and implement the algorithm, because we know that for large data set, if it gets stuck forever, then that program is no good. So let's take an example here. Suppose you have an inventory. And this inventory processes every transaction in every store in the United States of America. And suppose this guy makes 10,000 milliseconds to read the inventory. From the disk. And it takes 10 milliseconds to process each transaction. And if now you have n transactions, then what would be the time taken to finish all these transactions? What would be the time taken to finish all these transactions? So it's going to first read, so that it will be time taken to read the transaction, plus every transaction, it is taking 10 milliseconds to process, and there are n transactions, so it's going to be 10 times n. So our question here is not just about this. We are more interested. So this is kind of giving, okay, this much milliseconds, right? Our question is more tied with this n. As n becomes very large, so as n tends to infinity, what happens? So that would be the focus. And second important thing is that This unit of milliseconds is of course going to depend on how fast your computer is. Um, and then with the modern machines that we have got, there are multiple CPUs maybe operating on it. So all those details may be there, which are more architecture specific consideration. But here we are interested in analysis that is more target agnostic. It doesn't care about what architecture or what machine, how powerful your machine is that is being used for running the program. We are interested in analyzing in general what is the order of the number of operations. Therefore, we have to introduce some formal notions here. So let's define some terms here. The first term I would like to define is what is called big O notation. So big O notation represents the upper bound. So big O notation establishes actually an abstract relationship between two functions. Okay. So let n be the size of, I don't know what to do about this. My pen is kind of losing steam here. If I write it too fast, it is kind of messing up my handwriting. Okay, so I have to slow down. So let n be the size of your program's input. Now the size here can be meaning different things contextually. It can mean number of beds. It can mean number of elements or items. It can just mean some value. Like in the case of Fibonacci number, you wanted to find out the nth Fibonacci number. So there n represents the nth value. Okay. So here we are interested in computing an estimate of the running time of your program. So let's call that T of n. So let's T of n be a function this T of n is a function in the real world representing say, I mean, it does not have to only represent running time, because it is this theory itself can be applicable to something which is more abstract than the running time itself. But just for the sake of the context, we can use it for representing running time, because that is the interest that we have right now in analyzing the time complexity of your program. So let's say this is a function representing the running time. But keep in mind that the theoretical foundation that we are laying down, it can represent anything. So running time in that sense is just an example. And what are we trying to do? We are trying to establish relationship between this running time function and another function that can closely represent the characteristic of the running time as the number of inputs grows really, really large. So therefore, we are just interested in establishing an abstract relationship between the Tn, which is the running time, and another function um, which we can understand how it grows in general. Like for example, another function can be just a linear function. So when you are thinking about a linear function, you know that as so suppose this is f of n and this is n, right? A linear function typically grows like this, right? So as n grows, we can see that it grows linearly. So if I'm able to establish a relationship between Tn and a real and a linear function, then I know the characteristic of the growth of that function as n increases. And therefore, I'm interested in establishing this relationship between this running time function and another function whose growth I can reason about. I hope that is clear. So therefore, so therefore, the other function, so let f of n, so this is the another function that we are trying to relate with t of n, be preferably simple. So be another function that is preferably simple enough for us to reason about how it grows as n becomes really, really large. Is this point clear? Any questions so far? Because if you don't get this point, the rest of the theory will look like, why are we even discussing this? So I just want to make sure you understand the context, what we are trying to do here.
Wait, so just to clarify, so we're trying to understand the running time in terms of some like element n, but we're trying to understand it in terms of some like characteristic of it described by the function f or
Exactly.
something.
Exactly. So we are basically trying to establish a relationship between this Tn and Fn, where Fn is a preferably simple function which we can reason about as n grows to an astronomical proportion. Okay? Is that all right? Okay.
Wait, sorry. So Tn doesn't fully reflect Fn. Like there's more components to T of n other than Fn, right?
So the more component aspect is that we are trying to get a bound for the Tn. Like we are trying to see how to actually bind the Tn with some functions. That's what we are trying to do. So I think hopefully it will become more clear as we move forward and give some more examples. Okay. So this is how formally we will define Tn. So Tn is considered to be an element of the big O. So big O is really big O. Big O of f of n. Okay. If, so now I'm defining this. Okay. I'm defining the big O notation. So Tn is an element of, you can think of this big O represents like a set of all such Fn which satisfies certain property. So if T of n is less than equal to some constant c times f of n. So here, So when, where, so when n is big, right, for some large constant c. Just write it properly.
Wait, can you clarify the left side of the if and only if statement again?
Left side, yeah, this
Yeah.
is what we are defining, right? The big O notation. We are saying that the running time will be an element of the big O of f of n, okay? So clearly this is representing a set of all such f of n, okay? Such that the t of n is going to be less than equal to a constant times f of n, okay? So this is for some constant c, okay? So the question is, how big is, so I didn't write that statement, sorry. So for some constant n, so this is whenever n is big for some large constant c. So question is that how big is big? So big enough to make t of n fit under c times f of n. Let's try to understand this, okay? So suppose, so on x axis we have n going, right? And suppose my running time is something like this. This is t of n, okay? So if I'm defining this as f of n, right? So if I multiply with a constant, this is c times f of n. So all this is saying is that as long as you can justify that this t of n for all values of n remains inside, right? Less than equal to, then we can say that t of n is an element of the big O of f of n. So let's take the inventory example here, okay? Just so that it becomes more clear, okay? Let's come back to that inventory example. So in the inventory example, what we have got is, now we are writing t of n. What we found was that 10,000 was the reading of the inventory plus every transaction takes 10 milliseconds, right? So 10 times n, right? But for us, this millisecond aspect is irrelevant, right? With this 10,000 exact value, 10,000 exact value, 10 is sort of irrelevant in one sense. So we are trying out, let's say, f of n as n, okay? Because this indeed looks linear, right? So we can take here n. All right. So what is n going to be here? So n is going to be, this is your n, right? So suppose I pick c is equal to 20, then c times f of n is going to be what? 20 times n, right? So where is the 20 times n going to be coming here? How would the plot look like? 20 times n. So typically when we have to see what is 20 times n, so when n equal to 1, we see 20 rising here, right? N equal to 2, it goes to 40, like that, right? So it's going to look something like this, right? So this is going to be our 20 times n curve. All right, so then when we put the value of 1000 into it, into n, what do we get? So this becomes 20,000, right? So let's plot this first. Actually, let me just drop this first. First, let's try to plot the t of n first. It would be easier to. So this f of n is n. Okay. So let's first try to plot this. Okay. So here we find the, if the value is, say 1000, then the tn is going to be, let's say this is 20,000. And the y-intercept for this is going to be n equal to 0, then it's going to be here 10,000. So this curve goes something like this, right? It's a positive slope. So this is the plot for t of n, right? So when the value of n is 1000, what is the value of c of fn? It's going to be 20,000, right? So therefore, this guy cuts through here. So this is your 20 times n plot. Okay, is that clear?
Do we not care about the beginning portion of the graph where it's like lower than the function we're trying?
Right. So basically we are trying to see for what value of n we are finding that the cn is coming under, right? So let me just so this is 20n, right? This is our f of n, and this is our t of n. So what I'm trying to show is that beyond this point, right, t of n is always under f of n, but before that, that is not true, right? So therefore, what we are getting here is that for any n greater than equal to 1000, right, we got t of n to be less than equal to c times f of n. And we established by just picking c equal to 20. And therefore, we can say here that t of n is an element of big O of f of n. Or we can specifically say T of n is an element of big O of n. So now let's go back to the definition here. So this is essentially, we are choosing, you can see, for as long as we can choose some constant value, right? And we can come up with this as the upper bound for T of n, then we can say that the T of n is indeed an element of the order of f of n. Because after all, I'm interested in the large n, right? So n tending to infinity. So my interest is in large n, right? So what happens beyond some big number? So I just want to establish first conceptually what we are trying to do here. So for us, that n becoming large is the key for us to analyze the complexity. Any question on this? Anything you are not able to follow here?
You're basically saying so for the runtime function, there's sets of the functions in O such that T of n is less than f of n until
Less than equal to. Equal to is impossible.
C times f of n when n's less than or equal to 1,000. But we're trying to see like beyond that, what would happen basically, right?
C is equal to 20, n is greater than equal to 100. So we are reasoning about for large n here, right? That's the key here. And we are able to pick any reasonable value of C to establish the point that indeed the T of n is going to be less than equal to the C times f of n for any n that is greater than 1000. And that's great because I care about essentially what happens when n becomes large. Is that clear?
Yeah, thank you.
Good. All right, so now we are ready to define it formally. So far I was just trying to informally approach, just to give you a feel for how the notation looks like and what it actually conveys. So we can now say the order of f of n, okay, is the set of all functions. It's a set of all functions T of n that, you see why it's a set of all kinds of T of n, because you can come up with many such T of n, right? For which the T of n is upper bounded by the C times f of n. So there are many such T of n. So it's the set of all functions T of n that satisfies the following, that there exists a positive, no, not a positive, but there exist positive constants C and n such that for all n greater than equal to capital N, T of n is less than equal to C times f of n. So this is the definition of big O. So this is what is being referred to as big O notation. So here in the above example, you saw that this n was 1000, right? And C was 20. in the above example. Okay. Okay, let's take more examples here.
I have a question about C.
Go ahead.
We don't care about the actual value of C, right? It's
No.
just in the definition, like when you're answering a big O complexity problem.
Yeah, correct. We really don't care. In fact, after having formally defined this, you can see pretty much when you see a linear function, right, like this, you can imagine you can always come up with a value of C that can be larger than this, correct? Because you have to just pay attention to this guy, right? This is 10n. And 10 is representing essentially the slope, right? It's the y equal to mx plus c, right? Like or mx plus b, however you're familiar with. So 10 is representing the slope. And just by increasing the slope, you can see that you can put it at a higher level. That's another way of seeing it mathematically. So we chose c equal to 20 because that creates a larger slope. And slope means it's going to grow faster compared to this one. Does that make sense intuitively? So therefore, you can always come up with some c as soon as this is having a constant times n. All right. Let's take some examples. So the first example is that suppose you have 1 million times n is an order big O of n. So what is the proof here? The proof here is very simple. You just choose C equal to 1 million, right? And choose n equal to 0. So in other words, exactly what you said, that big O notation does not care about the constant factor. So what kind of constant factor you choose, that's completely up to you. So basically what we have done is that with this, we have abstracted out algorithmic speed independent of the underlying architecture. So architecture, there are many things that comes at play, right? Architecture, OS, and compiler. All of these come together to give you a certain measurement of speed. But our analysis is sort of independent of all of these architectural considerations. Therefore, it is unnecessary to write big O of 2 of n, right? Because we are not interested in this constant factor effectively. Second, so n is an element of big O of n cube. So if you draw the n cube, so n cube typically, like as you know, like when you increase the order of the polynomial, it grows more and more sharply, right? The growth becomes sharper. So typically, let's say we draw n cube, where this is our 1, right? This is our point. This is 1, this is 1, right? So this is your n cube, the plot for n cube. What would be the plot for n equal to, the function n? It's going to be this, right? Passing through this. So this is a linear function n, right? So you can very clearly see that after some point, after this point, n is always going to be very sharply higher than n, right? So here the proof would be very simple. If you have to prove this, that you just set c is equal to 1, right? And capital N equal to 1, because beyond this point, the n cube is always higher than. So therefore, this is a very important point. Therefore, if we say that running time is big O of n cube, does not mean our algorithm is slow. Why? Because big O, as you can see, is simply representing an upper bound, but it is not very strict upper bound. That makes sense? It is simply representing an upper bound. And therefore, you can make it n to the power 4, you can make it n to the power 5. They're still going to grow at a higher level than n. So in other words, this big O notation has not yet resolved our problem of measuring the speed. So when you take this n cube plus n square plus n, right? You go for the highest order polynomial and you will get order of big O of n cube. And here the proof is again very simple, where you set c is equal to 3, 1, 1, 1. So 3 and then capital N is equal to 1. And you can plot this. Like if you plot this, you can see that essentially n will be here, n square will be here, n cube will be here, right? And if you add them together, then you can it will be growing faster than n cube, right? So big O, so let me be very clear. So what this means is that we can say something is fast, but cannot say something is slow based on the big O notation. Cannot say something is slow, right? Because it is just acting as an upper bound. I drew here something wrong here. This doesn't make sense. Let me just correct this. So here, so this is your n, and this is going to be your n cube, and therefore the n cube plus n square, as far as this is concerned, this n equal to 1. So this is going to become 3 if you are making it n cube plus n square plus n. I hope this makes sense.
Wait, so we're trying to prove where the two functions like are equal, and then like beyond that we don't really care? Like, is that the point? I'm a bit confused about, like, why do we not care beyond when c is equal to 3?
In this case, what are we trying to establish? We are trying to establish n cube plus n square plus n, right? This is upper bounded by less than equal to c times n cube, right? So here, what we are interested in is if we are making it 3 times n cube, right? Then this would be sort of upper bounding these 3, right? Because this is a lower order polynomial. Does that make sense?
Yeah, that makes sense.
Right. So here we are just saying that if you are picking on the largest order polynomial, you can grow this constant to a level that it just exceeds whatever the contribution that can come from the lower order polynomial. That's all I'm trying to show here. Okay. So overall, the point that I'm trying to drive home here is that the big O notation is usually used to indicate the dominating or the fastest growing term. So in this case, the fastest growing, you can see, right? Like the fastest growing term is going to be the n cube. And therefore big O notation clearly is going to be picking on the fastest one. Any question? Is it clear? So now if I were to just write a table of important big O sets, I'll just conclude our discussion for today with this table of important big O sets. And I'm representing from smallest to largest. Okay. So I have your function, and this is the common name that is used for representing that function. So the smallest one is order of 1, right? Because if you draw in a graph, you can draw the constant something like this, right? And then if you draw an n, it will be going like this. So clearly at any given time, this n would be always growing faster. So in this way, the sequence in which it follows is that this is smaller than order of log n, okay? And this is smaller than big O, okay, of log square n. This is smaller than big O of square root of n. This is smaller than big O of n. This is smaller than order of n log n. This is smaller than order of n square. And then this is smaller than, of course, any higher order polynomial. And then this is smaller than the exponential. So these are the commonly occurring functions when you are trying to evaluate the running time. Okay, so they have different names. So this is called constant time, right? This is called constant. So when your program is coming out to be big O of 1, then we say that the program is running in constant time. When it's log n, this is called logarithmic time. This is log squared. This is root n time. This is linear. This is n log n. This is typically just called n log n. This is a very commonly occurring function. In fact, if you are able to get to this, this is the kind of, you can say, optimal sort of. Beyond that, if you're going here, the algorithm is practically useless for large n. So this is quadratic complexity. And then this is exponential complexity. So this is the area where your algorithm could be useful for large n. This is practically useless. And of course, you can extend this further, the 2 to the power n further, e to the power n further, n factorial further, n to the power n. And these are all useless area. So anyway, so for our purpose, we can actually try to see how to make our algorithm remain in this range and not go beyond it. Any question? You still are not done with the complexity theory. There's still some bit of discussion pending. So we'll continue next class, but today we will break for our lab. But I wanted to ask one last time, do you have any question?
Could you explain why it's useless after the n squared?
Can you say that again? What?
Could you explain why like the big O would be useless after
Yeah.
n squared?
You can imagine if your program has got 10,000 inputs, right? So that would kind of, if it is quadratic, that would amount to 10 to the power 8. So you can see how it grows, right? That makes sense?
Right, so you're saying like the
So
program can't keep up beyond that, or like what
He's saying
does-
the program is useless, not big O notation, right, Professor?
can you repeat that again? Can you say that again? There was a voice. I just couldn't follow.
I think what Professor
I think
was saying was that not the program would be useless because it's slow, not because the big O not big O notation is useless.
I was just saying that if you are evaluating, so here obviously we have to introduce another order notation. So obviously, as I mentioned, that we cannot comment
Oh, okay.
this point we have to keep in mind that the big O is simply upper bound, right? So if you're giving a very loose sort of upper bound, then this point is not so valid. I mean, later on, we will define a more tighter bound, which will come to the big theta notation. I think that would be a more appropriate comment, because one may define a really loose upper bound, then this point is not going to be valid. But if you have a tighter bound, which we will define in the next class, of n square, that essentially would mean, like, if your size of n is 10,000, the number of operations that you are performing approximately will grow to 10 to the power 8, which is a huge number. And you can see, like, as you grow to larger and larger value of n, doing so many operations is quite a large number. Now, one may justify the quadratic algorithm in this way, that one may say that in practice, my n is typically less than 100. Okay, my program is such that, like, or the specific application is such that the value of n is always less than 100, right? In which case it's fine with the quadratic algorithm. But here I'm just arguing that as n becomes really large, right, then any algorithm that is below this point is useless when the bound is a tighter bound than a loose bound that we defined using the big O notation. Is that point clear?
I kind of had a follow-up question.
Go ahead.
So is that to say that something like, I mean, wouldn't something like a nested for loop technically have n squared complexity, which I guess you're saying for something like 100 elements is fine, but if you're reading,
Yeah,
you know, thousands and thousands of pieces of data with a nested for loop, you're gonna have to iterate like n squared times.
Yeah, this is a useless algorithm. If you are hitting this kind of algorithm, this is a useless algorithm. That's exactly what I'm saying.
Should we just like avoid that in coding then?
It's not about avoiding that in coding. You have to come up with a more sophisticated algorithm. You know, it's not about just coding here. It's about coming up with the right combination of data structures and algorithm to avoid the change. And that is the art that we are going to study here in the data structures course.
Okay.
And right now I'm just pointing out why we are fighting so hard to come up with a data structure. One can easily come up with the worst possible algorithm for solving a problem. But that is not the goal of a computer scientist, to just coming up with just an algorithm to solve a problem. But one wants to come up with an algorithm that can function with large inputs, which is in real life, that's the most common situation. Okay. Okay, let's conclude and shift gear to our lab. Let me just stop the recording.